This video will go over the problems that I gave you guys last Wednesday and Thursday. I'll show you the answers to what you guys are working on Friday, and then give you some more review at the end. As far as AP updates go, I'll also have this typed in on the post that I'll send to you guys. Right now, they have told me that they're sort of cutting the material for obvious reasons. So you guys will just be tested over up to differential equations, so everything that we're working on now. I'm still going to continue to give you a variety of multiple choice and free response questions. As of right now, I don't know the makeup of the exam that they will be giving you guys, other than I think April 3rd, they said they'll have more information to come. So the material we cover in Chapter 7 is normally tested on the AP exam, but they are omitting that, but we still have to cover it. So right now, let's just take a look at these problems, and like I said, I'll give you guys more information as it comes to me. All right, so this problem was done without a calculator. For part A, we're given a differential equation. We just want to find a solution to y equals f of x to this differential equation, satisfying the initial condition f of 0 is equal to 1/2. So if we first start our derivative, dy over dx is equal to 3x squared over e to the 2y. So also keep track of your points as you follow along with the work you did. You get 1 point right away for separation of variables, so I just want to multiply both sides by e to the 2y, and then we'll get 3x squared times dx. So just 1 point right here at this step. After this, we want to take the integral of each side. Now, technically, we could use substitution. Remember, that's just a tool to help us if we can't figure out the antiderivative any other way. But hopefully, with the powers of e, you guys have found this to be a little easier than others, that we could just take the integral here. It's going to be e to the 2y, but we need a 1/2 in front of it, because when we go to take the derivative of this, we need a coefficient to be 1. So derivative of e to the 2y is just e to the 2y, but then times 2. So to get that 2 to go away, we'll put the 1/2 out in front, plus our first constant, and then over here we'll just have an x cubed, or really it comes from 3x cubed over 3, and then those 3's divide out, and then we get plus our second constant. I'm just going to combine the constants, so we'll get 1/2 e to the 2y equals x cubed. Really, I'll call this c sub 3, because next we have to multiply both sides by that 1/2, so it's yet a different constant at this point. So we could say e to the 2y is going to equal 2x cubed. Now at this point, I think I could just call it the overall constant. It shouldn't be changing anymore. What we want to do next is take the natural log of each side. And you would get a second point, actually a couple steps back. It's actually saying 2 more points for this step right here, for taking the integral of each side and including the constant. So you would get 2 more points there. 1 point for reaching this step, so 4 points right there. So next, what we want to do is just say this becomes 2y equals, I don't know why I wrote that as an exponent, this part right here. Technically, that should be in absolute value bars, but since it's just looking for a solution, I'm really not going to write it that way. So in the next step, I'll just write this as the natural log of 2x cubed plus c. Now, if we weren't asked for part B, which is to state the domain and range, then yes, I would still keep the absolute value bars around it. So now y is going to equal just this natural log, we could say 1/2 times the natural log of 2x cubed plus c. But really don't get any more points from this part of it. You get the 4 points right up into this step. Now to satisfy that initial condition of f of 0 is equal to 1/2. We'll just say 1/2 is going to equal 1/2 times the natural log of 2 times 0 cubed plus c. So if we divide both sides by 1/2 or multiply both sides by 2, we'll just get 1 is equal to the natural log of really just c. And then we'll use a base of e on each side. So c is really going to equal e. Therefore, we could say that y is going to equal 1/2 the natural log of 2x cubed plus e. So there's a solution that we're looking at. Again, whether or not you keep the absolute values around here, it's not going to matter. Because of part B, we want to state the domain and range. And because we're stating this, we're making sure that this expression 2x cubed plus e is going to be positive. So if you state that here, you get 1 point for indicating that you understand this. All right, so going back to this other part here, you get 1 point for determining what C is and then 1 point for the answer. So right now we're up to 6 points. Part B, and 6 points is a very good score to get on a free response question, but for Part B, it's not much more difficult to get the full 9 on here. So you get 1 point for indicating that you know that what's inside those parentheses there has to be positive, and then you would just set 2x cubed plus e has to be greater than 0, and then solving for x. So we'll get 2x cubed has to be greater than a negative e. X cubed has to be greater than negative e over 2, and then x has to be greater than the cubed root of negative e over 2. So our domain pretty much is this. You could leave it just like this, or you could just indicate that it's going to be from the cubed root of negative e over 2 to infinity. So you get 1 point for stating that. Now, as long as what we're substituting in works here, we have no other issues, so our range is actually going to be all real numbers. And you get your 3rd point from that. So there's where all 9 points come from. All right, next we're looking at the multiple choice questions here. All right, so for number 1, and again, these are all no calculator. Again, we're given a limit definition of a derivative, so rather than doing any work with this, what we pull from it is our function. So our function comes from this, because remember, it's f of x plus h minus f of x, and then it's all over h. So this part right here is where we get our function, saying that it is equal to cosine x. Then we take our derivative, because as we take the limit of this function as h approaches 0, that is the definition of the derivative. So f prime of x is going to equal a negative sine x. And then we evaluate this now with this 3 pi over 2. So f prime of 3 pi over 2 is just going to equal the opposite of sine of 3 pi over 2. So it's the opposite. Sine of 3 pi over 2 will give us a negative 1. So we get a positive 1, which is where we're getting A as our answer. All right, for number 2, here it gives us the information. Our first derivative, so dy over dx, has to be negative, which means our function, we'll just say, we'll call it y, is decreasing then. And where our second derivative is also negative, that tells us that y is concave down. So if we put both of these together, I just want to discuss what's happening at each point. So at point A, the graph of our function is concave down, but our graph is increasing. So that's what rules out A. B is the correct answer, because at this point, our function, our graph is decreasing and concave down. Looking at C, we're actually concave up, so that just rules it out. We're still decreasing. At D, we can argue that that looks like it's a minimum, but regardless, we're still concave up. And so at E, we're increasing and concave up. So that's what makes B the correct answer. It meets both of those conditions. All right, for 3, we have to use implicit differentiation carefully. And we want to evaluate y prime when we get to that part at 2, 1. So looking at this first, we have to use the product rule, this first term. Let's go with uv prime, so that becomes y cubed times 1 plus vu prime, so it's x times 3y squared, but then y prime. Our next term, y squared plus x squared, so uv prime becomes y squared times 2x plus vu prime, so x squared times 2y, y prime, and then that's going to equal 0. Just to make it a little bit easier to work with, I want to pull all these coefficients out in front, so we'll get y cubed plus 3xy squared y prime plus 2xy squared plus 2x squared y, y prime. And we'll keep the two y prime terms on this side, so 3xy squared y prime plus 2x squared y, y prime equals a negative y cubed minus 2xy squared. Factor out a y prime. We will have 3xy squared plus 2x squared y equals negative y cubed minus 2xy squared. All right, so y prime is going to equal negative y cubed minus 2xy squared all over 3xy squared plus 2x squared y. So now at 2, 1, y prime is going to equal the opposite of 1 cubed minus 2 times 2 times 1 squared all over 3 times 2 times 1 squared plus 2 times 2 squared times 1. So this will give us a negative 1 minus 4 up top, and then a 6 plus 8 in our denominator. So y prime is going to equal negative 5/14, giving us C. So hopefully you guys were able to do pretty okay with those problems. All right, for these, we were able to use a calculator. Taking a look at 78 is a related rates question. Our radius of a circle is decreasing, so we could say that dr over dt is actually going to equal a negative 0.1 centimeters per second. In terms of the circumference C, we want to know what the rate of change of the area of the circle is. So we want to find dA over dt in terms of our circumference. So notice it doesn't really give us a full amount of information to find it at a certain point, but it just wants us to write it in terms of the circumference. So we also need to know that circumference is equal to 2 pi r, but we need to relate area to our radius. So the equation we're going to differentiate is area equals pi r squared. But looking at this in terms of our circumference, we're going to need to replace that radius. So radius is equal to c over 2 pi. And then if we differentiate the area formula with respect to time, we'll have dA over dt is equal to 2 pi r times dr over dt. So this will become 2 pi times our circumference over 2 pi. And then dr over dt is a negative 0.1. So dA over dt is going to equal the 2 pi's divide out, and we're left with a negative 0.1 c, and that's where we're getting B from. All right, for this one, we have seen this before. I assigned it before, and it's still good to always go back over and check. The graphs of the derivatives of the functions f, g, and h are shown above. Notice each one says f prime of x, g prime of x, h prime of x. Which of them have a relative max? So we only get a relative max when the first derivative changes, because we're looking when our graph changes from increasing to decreasing, so changes from positive to negative. Remember, we don't want to say when the first derivative changes from increasing to decreasing. That is our function. So our function changes from increasing to decreasing when our derivative changes from positive to negative. So if we go and take a look at the first graph here, all of these values are negative from a over, so looking here, we have negative value, so f prime of x is negative, and then right up here, it changes to positive, and then we're back to negative here. So we actually have right here is where a relative, no, looking right over here rather, is where we have a relative max. When we're changing from positive to negative, we have a relative max. For g of x, everything over here is negative, and then we change to positive. So actually changing from negative to positive, this will give us a relative min right here. And then if you notice for the graph of h prime of x, all of these values are positive. So there is no change, no maxes or mins for h prime of x. So that's what makes A, F only our answer. All right, 85 I kind of wrote out ahead of time here because there was a lot to write up but not really a lot to say about this. We're looking at a trapezoidal approximation. So the area of a trapezoid, remember, is 1/2 the height times the sum of the two bases. So the reason I had to write this out 3 separate times is because if you look at the differences between the x values here, we have a difference of 3, and then we go 2, and then we go 1. So we can't just write the rule, the trapezoidal rule for this. We just have to find the area of the 3 different trapezoids. So this integral's approximation is 1/2 times our height, or the distance between 2 and 5, so 3, and then times the sum of the two bases, so 10 plus 30. The second trapezoid is 1/2. Our distance between the two x values is just 2. Then we're adding the 30 to 40. And then our last one, we have 1/2 our height, or the distance between the two x's is just 1, and then we add 40 to 20. And then calculating this just gives us 160. So even though you were allowed a calculator, you shouldn't have needed one for this one. All right, looking on page 338, the first problem here, let me just go back to the book to read the directions. All right, so a lot of these I have written out ahead of time just to go over them. But for number 1, we were given a differential equation, dy over dt is equal to ky. Remember, anytime we're given that, we can just show that the solution to this is that y equals that initial amount times e to the kt. As I showed you before, there's so many different ways to write this. It could be y equals p times e to the rt, or a equals p times e to the rt. So it all depends on what our problem is about to show which form we're going to use, and a couple forms are correct using them for the same problem. So number 1, it tells us k is 1.5, and then that our initial condition y of 0 is equal to 100. Well, our initial condition is always going to lead us to that value of a, and I'm just showing that work here. So if we did say y of 0 is equal to a times e to the 1.5 times 0, we would get a is equal to 100. So we could just go straight to this answer that y is equal to 100, e to that 1.5 times t, because k is 1.5. Number 3 was a little different. They gave us 2 initial conditions. Again, notice I'm showing that dy over dt is equal to ky, because that applies to all 4 of these problems. Therefore, y is equal to a times e to the kt. Notice I didn't really even put that a sub 0 there for the initial amount. All right, so what we want to first find here is what is a. And again, y of 0 is 50, so we could just jump to this line, but I'm still showing you that a is going to equal 50, therefore y is equal to 50 times e to the kt. Our next condition, because we don't know what k is, we have to find it, y of 5 is equal to 100. So now that I know what a is, I can now put in 100 is equal to 50 times e to the 5k. So t is 5, so that's where I'm looking at up here, k times t. And then this allows me to just divide both sides by 50, take the natural log of each side, solve for k, so I'm leaving it as an exact value, and our overall solution for this is y is equal to a, which is 50, e to the k times t, and k is that natural log of 2 over 5. I just put it in parentheses to just show that all of that is the exponent. All right, for number 5, this is where I'm actually using that a equals p times e to the rt, because we're talking about money that is compounded continuously. So we always want to show our plan. So I'm writing out that a is equal to p times e to the rt. I want to find the doubling amount. So whatever the initial amount is, p is, a is just going to be double that. So for a, I just wrote in 2p is equal to p times e to the rt, because next our p's divide out. So I just get 2. So no matter what amount we had initially, the doubling amount will always simplify to just 2 equals e to this 0.086. That's what our rate was, times t. Again, take the natural log of each side. Exact answer is natural log of 2 over this 0.086, or approximately 8.060 years. For part B, we just needed the amount in 30 years. So I go back to this problem. Since we know our rate and the initial amount here is 1,000, we could just say a of 30 is equal to 1,000 e to the 0.086 times 30, a straightforward calculation, getting the 13,197.14. All right, looking at 7, our initial deposit is missing. We're given our annual rate of 5.25%, and we're given the amount in 30 years, so we also have to find the doubling time. So I'm first going to find the initial amount, obviously, because we need to know that before we try to double it. So what I do is I substitute an A of 30. So 30 is going in for T. I already know the amount. We just need our principal amount. We know what the amount of 30 is, or at 30 years is. So we have this 2898.44 is equal to P times E to the 0.0525 times 30. And P is just equal to that amount at 30 divided by E to that exponent that's there, and we should get exactly $600. So when I go to figure out the doubling time, that means I want to know when it's going to get to 1200. So here again, if I divided the 1200 by 600, I get 2 is equal to this E to that power, 0.0525 times T. Take the natural log of each side. So T is equal to natural log of 2 over that should be a 0.0525. And that's approximately 13.203 years. All right, now number 12, there was quite a lot going on here. That's why I gave you guys a couple days to give this a try. This one I am going to show step by step as I explain. All right, so we're given at the end of 3 hours, this is a bacteria growth problem. At the end of 3 hours, there's 10,000 bacteria present. And at the end of 5 hours, there's 40,000. We need to figure out how many are initially present. Notice we don't have K. We don't have an initial amount either. So let's first go ahead and find K. Now what I'm going to do here is just sort of set this up, substituting in. So if I know Y of 3 is equal to 10,000, that means I could set 10,000 equal to A times E to the K times 3. I'll write it this way first. And then over here, Y of 5 is equal to 40,000. I've got 40,000 is equal to A times E to the K times 5. So what this allows me to do is solve for A. So A is just going to equal this 10,000 divided by E to the 3K. And then over here, A is going to equal 40,000 divided by E to the 5K. Now, since both of these initial amounts A have to be the same, I could just set the two expressions equal to each other. So 10,000 over E to the 3K is going to equal 40,000 over E to the 5K. So I could do all this without knowing what that initial amount is. Solving for K, I'm just going to multiply both sides by E to the 5K, then divide by 10,000. So this turns into E to the 5K over E to the 3K, because I could do something with that next. And then 40,000 divided by 10,000. So going back to laws of exponents, I could just subtract the exponents when my bases are the same. So I get E to the 2K is equal to 4. We'll take the natural log of each side. So 2K is equal to the natural log of 4, and K is equal to the natural log of 4 over 2. So I have K. Now, to find the initial amount, I can go back to either one of these two equations I wrote out. I'm just going to use this one over here. So we're going to say A is equal to 10,000 divided by E to the 3 times K, which is now the natural log of 4 divided by 2. And then this gives me, not approximately, but 1,250. So that's the initial amount. So 1,250 bacteria initially present. So the tricky part with that one was just knowing how to get started and how to use that. All right, and then for number 13, even though it was right after 12, you think it would be as complicated, but not so much. All we had to really do, they gave us a nice equation to start with, and this was talking about radon 222, about how long will it take the amount of radon in a sealed sample of air to decay to 90% of its original value. So that means when 90% is left, we don't have to do the 10% is left. That would be when 90% is gone. But this is saying 90% of its original value. So 90% is left. So all I have to do is set the expression equal to 0.9, because if our final amount is 90% of our initial amount, we could just jump straight to this. So then we take the natural log of each side, solving for t, natural log of 0.9 divided by a negative 0.18, giving us approximately 0.585 days.